Seismologists from all over Japan are focusing on this area 100 kilometers south of Japan's main island of Honshu. Investigators are using sound waves to explore the structure of the seabed. They're looking closely at the tectonic plates that lie beneath Japan. Concerns over a major earthquake in the Nankai Trough are now rising throughout Japan. The enormous seismic source area spreads directly under the Japanese archipelago. Researchers have discovered eerie vibrations that frequently occur here. A high-performance seismometer captured those vibrations 3,000 meters underground. Tiny tremors that humans can't detect are created by underground movements called slow quakes. Unlike typical earthquakes, these small vibrations go on for a long time. For 600 kilometers from the Tokai region to the island of Kyushu, these vibrations are being recorded all around the Nankai Trough.
These earthquakes are rather strange. They continue non-stop for 24 hours straight.
A major earthquake in 2011 has been a focus of attention. Investigators found that a slowquake had occurred immediately before. A slowquake may signal that a major quake is imminent.
These quakes might be signaling that the next major quake in the Nankai Trough is near. We want to collect as much data as possible.
Megaquake. The Nankai Trough is certain to be the source of one in the near future. But we still can't predict how big it will be. Scientists are now trying to find out. When will the megaquake occur? Scientists are studying slowquakes to determine how they work. The latest technology tracks the Earth's movements and brings to light the crisis unfolding beneath Japan.
It seems preparations are in progress beneath our feet for the next megaquake.
New and unusual facts have also emerged. The seismic source area of the Nankai Trough may be expanding and moving closer to metropolitan areas. The massive tsunami that would hit Tokyo Bay would arrive just 10 minutes after the quake. People would have no time to evacuate.
It would be risky to take measures only against likely scenarios without considering other contingencies.
This megaquake series uses the latest technology to unravel the mysteries of earthquakes and examine emerging signs of an impending megaquake in the Nankai Trough. Japan is surrounded by 4 tectonic plates. The Philippine Sea Plate is one of them. It's been sinking under the continental plate by a few centimeters every year. The plate begins its descent at the Nankai Trough. The source area between the trough and the boundary of the plate stretching under Japan has caused repeated major earthquakes. The Philippine Sea Plate pushes against the continental plate. Pressure there is building. When that pressure becomes too great, the entire continental plate will suddenly shift, causing a major quake. The Japanese government has declared the Nankai Trough earthquake one of the country's biggest disaster threats.
We use the phrase national crisis, and we believe such a disaster could happen.
The magnitude of the quake could be as high as 9.1. Areas from the Tokai region to Kyushu would be hit by severe quakes rated 7 on the Japanese scale of 1 to 7. Towering tsunami over 10 meters high would hit the Pacific coast. Two of Japan's 3 main metropolitan areas, Nagoya and Osaka, would be crippled. In the worst-case scenario, 320,000 people would die. The country would face a crisis. There have been numerous major quakes in the Nankai Trough.
50トン近くの大漁船が海岸から数丁も離れた道路の上にのし上げて津波のものすごさを語っています。
The last major quake in the Nankai Trough happened 67 years ago. At the time, the country was in a state of post-war chaos. Hardly any scientific data remain to help us predict the next megaquake. The next megaquake is inevitable. Is it possible to use the latest technology to predict when it will happen? A network of 800 seismographs has been set up across Japan. These highly sensitive devices will capture even the slightest vibrations occurring deep underground. Using such wave patterns as clues, one scientist is trying to discover signs of an imminent megaquake. He's Kazushige Obara of the University of Tokyo. Professor Obara has studied the Nankai Trough for many years. 13 years ago, he found a strange vibration amid the output of a highly sensitive seismograph.
At first glance, it looked just like the usual noise. But if you look here, it continues for about 4 minutes.
An analysis of the wave patterns showed that the strange vibration was different from those produced during a typical earthquake. The purple line is the wave pattern of a quake. The tremors quickly grow larger and eventually subside. The blue line, on the other hand, is the strange vibration Obata found. It appears to be straight. But magnifying it 1,000 times reveals minute vibrations. These tremors that are too small for us to feel can continue for days or weeks. The underground movements that create these lengthy vibrations are called slow quakes. Where are these slow quakes happening? The yellow dots indicate where they're occurring. The red areas show the seismic sources of past major earthquakes. The vibrations from slow quakes were happening 5 to 40 kilometers underground in areas surrounding the seismic source areas.
I knew something had happened underground, since these slow quakes were happening in areas around the seismic sources of major quakes. I thought there might be some sort of relationship between the two.
Vibrations from slow quakes continued to be recorded after that. But their relationship to megaquakes remained elusive. What exactly is a slow quake? Here's what Professor Obata thinks. In a typical earthquake, pressure builds in the continental plate. When it becomes too great, the entire plate shifts. In a slow quake, however, a plate that's under pressure shifts slowly over time. The tremors from this type of shift are minute. That's what causes the strange vibrations. Slow quakes gradually release the pressure built up in the plate. That's why Professor Obata once believed major earthquakes were unlikely to happen after slow quakes.
I thought it was just a way to get rid of excess energy. Since it doesn't affect us directly, I thought we should be thankful it was releasing pressure.
But after the devastating magnitude 9 tremor which struck off the coast of the Tohoku region, an expert found that a slow quake had occurred immediately before the major quake. The person who made the discovery was Yoshihiro Ito. At the time, he was a researcher at Tohoku University. Four months before the major quake, he'd set up a seismometer in the ocean off the coast of Tohoku. Data retrieved after the earthquake revealed new details. The tremors of the slow quake began about a month before the major quake. They continued right up to the Tohoku quake.
I think the movement of the Earth's crust was triggered by the slow quake. The data suggest this is likely as well.
Why did the major quake hit immediately after the slow quake, which was supposed to release pressure? New facts have come to light. The slow quake occurred east of the seismic source of the major quake. It occurred at the boundary of the same plate as the major quake. The slow quake lasted for about a month and shifted the plate about 40 centimeters. Ito believes this large movement triggered the major quake. What really happened here? The oceanic plate was sinking under the continental plate. The two plates were stuck together in a wide area called an asperity. This asperity was the seismic source of the megaquake. Pressure built up there over a long period of time. However, some areas around the asperity were only partly stuck together. Every time the pressure built up, the plate moved, and those areas moved with it. That is a slow quake. It was believed that these movements released the pressure built up between the plates. But off the coast of Tohoku, the slow quake lasted about a month, and the plate moved 40 centimeters. Pressure in the asperity had become too great. It was pulled by the tremors of the slow quake. And the entire asperity shifted. That's what Ito's research suggests. This is a model of the relationship between slow quakes and megaquakes. On the top is the continental plate. On the bottom, the oceanic plate. On the left is the wide asperity, which is tightly stuck. And on the right is the partly connected area where slow quakes occur. The oceanic plate sinks at an even speed. When viewed from above, the asperity remains firmly in place. But the partly connected area is starting to shift. This is what a slow quake looks like. If this kind of movement continues over a long period of time, the asperity is pulled rightward, and the entire plate shifts. Plate movements caused by the slow quake are shown here in yellow. They are thought to have occurred over an area of the seabed stretching 100 kilometers north to south off the coast of Tohoku. This huge movement is believed to have moved the entire enormous asperity at once.
What's important this time is that we were able to record that happening. We discovered how slow quakes are caused. I felt we needed to reevaluate the relationship between slow quakes and major earthquakes.
Professor Obata has made discoveries about slow quakes in the Nankai Trough. He was shocked to learn that the 2011 quake had happened immediately after a slow quake. When might a slow quake trigger a major earthquake? Off the coast of Tohoku, where the seismic source was far from the land, hardly any data exist concerning the slow quake in 2011. In the Nankai Trough, however, movements can be tracked from land in real time. Over 10 years' worth of data have been accumulated. Careful analysis of the data shows that slow quakes exhibit a certain pattern. In Mie Prefecture, for example, slow quakes occur every 6 months. They last about 10 days. In the Shikoku area, they occur once every 3 months. And last about a week. There are patterns behind the occurrence and the duration of slow quakes in different regions. Are there any variations in these patterns? Obata thinks that tracking them will help predict when major quakes will happen.
I think there will definitely be a change in slow quake patterns before the next megaquake hits. I want to detect the differences in where and when they occur.
Wakabayashi Ward in Sendai was hit by the tsunami that followed the Tohoku earthquake. Professor Obata was born and raised here. His memories of that day continue to drive his research.
I was really upset that I was unable to find a way to prevent this disaster. Actually, I felt helpless. The only way I can contribute is by using my current research on slow quakes to try to predict the next megaquake.
Scientists around the world are stepping up their research into the slowquake phenomenon. This type of tremor has been detected in 10 areas so far. Among them are New Zealand, Mexico, and Alaska. Megaquakes are considered likely in these places. The area around Seattle on the west coast of the U.S. is another. In 2012, a change occurred in the pattern of slowquakes, raising alarm among researchers. The slowquakes were concentrated in the Cascadia subduction zone along a coastal plate boundary. Scientists fear a magnitude 9 level earthquake could hit the area. Cities would experience violent shaking. And soon after, massive tsunami would engulf communities along the coast. Dr. Herb Draggart has been studying the patterns of slowquake development. In this region, slowquakes happen about once a year. They last about 3 weeks.
It appears to be cyclical, and that's one of our challenges, is to see if the deviations from any cyclical nature means something else, something new.
Slowquakes had once been fairly regular events. But the pattern changed significantly in 2012. In late August, a slowquake started north of Seattle and spread 600 kilometers north and south. It was still going more than 3 weeks later. Concerns that a massive quake was imminent rippled along the west coast.
This current slow slip quake under the Salish Sea has lasted 5 weeks. Last year's great earthquake and tsunami in Japan was preceded by slow slip and tremor near the epicenter. University of Oregon professor David Schmidt makes an analogy.
Even though the nudge is small, at some point that nudge might be enough to kind of tip us over the edge and cause the car to fall off the cliff.
It was so long-lived and covered so much area. Yes, it caught our interest, and we were wondering whether it was going to stop here.
The slowquake lasted 6 weeks, twice as long as normal. But it suddenly stopped spreading, and the tremor gradually subsided. What caused the slowquake to change its pattern? Why wasn't it followed by a massive trembler? Dr. Draggart plans to analyze the effects of the tremor, also known as an episodic tremor and slip, or ETS, on the seismic source area.
We don't fully understand that relationship yet, but we are convinced there is a connection. We are trying to establish the relationship of ETS to the occurrence of large earthquakes.
Researchers are working hard to decipher subtle hints that could warn of a megaquake. Some are using global positioning systems in their research. There are some 1,200 observation points across Japan. Researchers use satellites to record slight movements of the Earth down to the millimeter. This image shows ground movements captured by the GPS devices. East of the Nankai Trough, tectonic plates shift in a complicated manner. The area is off the coast, south of the Kanto region, where Tokyo is located. The Philippine Sea Plate slides underneath the Nankai Trough. The Izu Island chain is moving north along with the underlying plate. But the Izu Peninsula is moving west. What explains the different directions when the islands and the peninsula are on the same plate? A researcher in southwestern Japan is trying to solve the mystery. He's Professor Takao Tabei of Kochi University. His research has taken him to a reef called Zenisu. It's about 80 kilometers south of the Izu Peninsula. He wants to find out which direction Zenisu is moving in. The cluster of rocks sits on the Philippine Sea Plate. He has brought a portable GPS device to measure the movement. Tabei has discovered that Zenisu is shifting toward the west, just like the Izu Peninsula. The red area adjacent to the Nankai Trough is thought to be moving in a westerly direction. Tabei thinks something unusual is happening to the Philippine Plate. He suspects the plate is split between the part that's moving north and the part that's moving west.
Here's where the boundary is commonly thought to be, but I think there's another border. It's being formed as we speak.
What is causing the tectonic plate to crack? Tabei thinks the Izu Peninsula is playing a part. The Izu Peninsula is on the Philippine Sea Plate. The peninsula is pressed against the continental plate, unable to move any further. The Philippine Sea Plate keeps getting pushed from behind. The intense pressure is causing the split. Tabei believes the Philippine Sea Plate is starting to sink along the split. The plate's new boundary probably runs about 50 kilometers east of the Nankai Trough. This would mean the source area of a potential megaquake has spread eastward, closer to the Tokyo area.
If a new plate boundary is created, earthquakes could occur around it. and they could generate huge tsunamis.
If the seismic source area has extended further east, a tsunami could hit the Kanto region sooner than previously thought. Associate Professor Ikuo Abe has conducted tsunami simulations to learn how they work. If a massive trembler occurred in the seismic source area that was previously suggested by the government, a tsunami over 10 meters tall could reach the Kanto region in little more than an hour. But what if the source area had spread 50 kilometers to the east and a magnitude 8 level quake occurred? It would only take 14 minutes for a 10-meter high tsunami to hit cities like Fujisawa and Kamakura in Kanagawa Prefecture, southwest of Tokyo. The wall of water would follow major roads and quickly reach the centers of those cities. People would have little time to escape. Most of the coastal communities would be flooded. "45 minutes after the onset of the quake, the tsunami would flow into Tokyo Bay. The 3-meter tall tsunami would reach the bay over 30 minutes sooner than previously predicted. It would cause major damage to the Kanto region's coastal areas.
There's still so much we don't know about nature. It would be very risky to take measures only against likely scenarios without considering other contingencies.
The threat of a possible megaquake along the Nankai Trough is becoming increasingly clear. A new study using GPS technology is underway. It's led by Associate Professor Takuya Nishimura of Kyoto University. His team is trying to accurately measure the strain building up along the Nankai Trough and the ground movement caused by slow quakes. Their goal is to predict the next major earthquake. The arrows show the movement of the land being pushed by the ocean plate. The longer the arrows, the stronger the force. GPS technology helps Nishimura measure the pressure that's being applied from the ocean side. Where the force is strong, both plates probably remain stuck together as they move, which could be causing strain to accumulate. The length of the arrows indicates how much strain has built up and where. By analyzing the data, researchers can identify regions of intense strain within the possible megaquake source area along the Nankai Trough. Here's the result. The red areas show a large buildup of strain south of Shikoku, the smallest of Japan's 4 major islands. Nishimura also used GPS technology to analyze in detail the ground movements caused by slow quakes. From time to time, some of the arrows become shorter. the timing coincides with slow quakes. Why do the arrows get shorter? Normally, the land is pushed from the ocean side. But when a slow quake occurs, the land shifts back toward the ocean. That's what makes some of the arrows shorter. In 2007, a slow quake occurred in Aichi Prefecture in western Japan. These arrows look shorter. In 2008, these arrows in Mie Prefecture, just to the west, were also shorter. And Nishimura noticed a big, possibly critical change. In 2006, a slow quake was recorded in Shikoku. It was one of the largest ever detected. It took place in the western part of the island. The Earth moved 1.3 centimeters toward the ocean in just one day. A month later, the land in central Shikoku moved 1 centimeter. Yet another month later, the eastern part of the island shifted 1.4 centimeters. Such a huge single-day movement had never been observed before. These significant ground shifts occurred near the highly strained parts of the seismic source area. If the movement continued, could it trigger a massive earthquake? The strain mounts as slow quakes continue to move the Earth. By monitoring these two types of geological phenomena, Nishimura hopes to be able to identify the signs of an impending megaquake when they manifest themselves.
It seems that preparations are in progress beneath our feet for the next megaquake. We will continue to collect many different kinds of data. If we can identify important clues, they'll be crucial for our efforts to predict a huge tremor. We will definitely continue our research in this area.
Salute! We're now going off to study ocean floor crustal movements.
When will the next megaquake occur? New efforts to find clues are underway. Japan's Coast Guard has increased the number of GPS observation points on the seabed around the Nankai Trough. They're keeping a close watch on unusual movements in the tectonic plates.
About 4 centimeters a year toward the northwest. That's quite a big shift.
Another study is in progress in an attempt to capture early signs of an earthquake. It combines advanced science and past records. The research focuses on something unusual that happened to well water right before the massive Nankai quake in 1946.
The water level dropped a lot. We had to tie more rope to the bucket to reach the water.
The researchers confirmed that the same thing happened in 15 other wells prior to the huge earthquake. They're beginning to suspect these incidents were caused by slow quakes. Right before the 1946 earthquake, slow quakes might have occurred frequently. The movement of the land could have caused the groundwater layer to spread, lowering the water levels in the wells. Experts suspect something similar may occur shortly before the next megaquake strikes. They are now monitoring some 60 wells across Japan.
Maybe only a fraction of geological changes can be observed above ground, but we must keep an eye on the wells so we can quantify any changes. Such opportunities are limited, and we have to grab them when we can.
Professor Obara continues to study slow quakes around the Nankai Trough. He's identified a new location where slow quakes have occurred. It's in the southeastern island chain, some 200 kilometers south of Kyushu. The area is further south than what's considered the southern end of the Nankai Trough.
This data could help us understand whether an earthquake in the Nankai Trough could also affect the southeastern island chain.
More clues about potential megaquakes may still remain hidden. Day in and day out, Obara reviews huge amounts of data.
Taking a close look at the data is the first step in identifying the signals the Earth is sending out. Usually, 99% of the information is meaningless. But if even 1% of the data turns out to be valuable, I think it's worth the effort to study these waveforms.
Megaquake. Japan cannot escape the threat of massive earthquakes. Will scientists be able to decipher the subtle signs the Earth is throwing at us and predict when and where the next megaquake will strike? They'll continue their battle, armed with their wisdom and expertise.